This webinar presents a direct initial cost comparison between steel and concrete short-span bridges. The purpose is to address the preconception that concrete is always less expensive than steel for short-span bridges. The lecture continues by examining the life cycle costs of typical steel and concrete bridges in the state of Pennsylvania. As mentioned in previous webinars, the Short-Span Steel Bridge Alliance was formed to address two main concerns with the construction of steel bridges. The first is a misconception across the United States that for shorter span bridges, concrete is always less expensive than steel. The second issue is that a concrete bridge is easy to design using charts and tables, whereas a steel bridge design is an individual piece of art for each designed bridge. Last week's webinar presented eSpan 140, an online tool for preliminary steel bridge design for simple span bridges up to 140 feet in length, so that steel and concrete bridge alternatives can be compared easily without an undue and costly design for the steel bridge. Here, we will look at initial cost case studies for county and state bridges to show the competitiveness of steel and demonstrate that the life cycle costs for steel and concrete bridges are also competitive. We start with that preconception that concrete bridges are less expensive than steel bridges in the short span market. Many owners and engineers believe this to be true, and many times steel is not even considered when there is a short span bridge need. Studies show that states or regions that do not even consider steel alternatives and only build concrete bridges pay more for those concrete bridges than states or regions that have a healthy competition between the two bridge materials. This is unfortunate because that means owners may be paying more for their bridges than is necessary. If owners and engineers would compete steel and concrete bridges, the cost for both would be lower due to the competition. We will now look at case studies of county and state bridges to show the competitiveness of steel. The first case study is from Audrain County, Missouri from 2012. Now, Dr. Michelson last week touched on this case study and a few more bridges there, but here we're going to go into it in a little more detail to really show the competitiveness of steel. These two bridges were built by an Audrain County work group, so there is no contractor for the bridges. This is a special case study in that the Short Span Steel Bridge Alliance worked with the county engineer from before construction through the opening of the bridge to track all costs. The steel bridge, Missouri Bridge 411, consists of 4 steel girders, a 47.5-foot span, a 24-foot roadway width, and a 2-foot structural depth. The concrete bridge, Missouri Bridge 336, consists of 6 precast hollow core slabs with a 50.5-foot span, a 24-foot roadway width, and a 2-foot structural depth. These two bridges were built in the same year and are nearly identical except for a small difference in the span length. The engineer was asked to keep a detailed account of the costs for the construction of the two bridges so that a direct comparison could be evaluated. This slide shows the total cost for the two bridges where the costs are broken into material, labor, equipment, guardrail, rock, and engineering. We can see that for the total cost of these two bridges, the steel bridge has a 19.3% savings over the concrete bridge. The costs are calculated based on the square footage of the deck area for an equivalent comparison, since the concrete bridge is 3 foot longer. However, comparing only total costs can be deceiving given the different site characteristics of the two bridges. For instance, here, we see that the concrete bridge had significantly higher engineering costs and lower rock costs, which has nothing to do with the actual constructed bridge. So to address these differences, the engineering and the rock costs are removed from the total cost to get a better comparison between the two bridges. When the engineering and the rock costs are removed, the concrete cost a little bit over 98 bucks a square foot, whereas the steel bridge had a cost of just over 83 bucks per square foot, or a 15.4% reduction in cost. However, we know there are still different site requirements that may influence the difference, such as roadway alignment work, approach work, grading and finishing, and other work. So the engineer was also asked to separate out only the superstructure costs so that an equivalent direct comparison could be made for the two bridges. In other words, track costs from when the superstructure went in until the superstructure was completed. So on this slide, these costs represent the costs associated with only the superstructure. This is a true apples to apples comparison of the costs for these concrete and steel bridges, since we could almost pick up the concrete bridge and put it on the steel abutments and vice versa. Removed from the total cost is all site prep work, grading, engineering, rock, abutments, and so forth. We can see the cost for the materials, labor, and equipment for only the superstructure. The steel bridge costs $37.5 per square foot, and the concrete bridge costs $50.61 per square foot. The steel bridge is considerably less expensive for this comparison. Now, one item to note is the equipment cost, where the steel bridge used a county-owned 30-ton crane. The concrete bridge girder members are heavy, and the county had to rent a 100-ton crane at a cost of $3,500. The other $500 for each under equipment was a rented skid steer for incidental work. However, even if the county needed to rent a 30-ton crane at a cost of about $1,500, that increases the steel bridge cost to only $38.88 per square foot, still considerably less than concrete bridge cost. Now, for the steel bridge, the steel girders are weathering steel that require no painting, and the weathering steel costs are already in the cost of the steel girders. If the county needed additional corrosion protection and used galvanizing, the cost is approximately 22 cents per pound of steel for the galvanizing, and the steel bridge cost would still be significantly less than the concrete bridge cost. So for these two bridges, as they were built, the superstructure only costs show that the steel bridge option would have a savings of over 25% compared to the concrete bridge. That is 5 steel bridges for the cost of 4 concrete bridges. This is for 2 almost identical bridges where they have the same structural depth, which means no difference in approach work, the same roadway width, the same guardrail system, the same abutments, and the same county crew built both bridges. So what this demonstrates is that steel is competitive with concrete. Here it's actually significantly better. But the objective here is to show that steel is competitive with concrete, and the preconception that concrete is always less expensive is incorrect. Short span steel bridges can have, and many times will be, less expensive than a concrete option. The reason for these economies for steel bridges vary over the bridge fabrication and construction process. For instance, we saw that one reason steel is competitive is that equipment requirements are less, since the steel bridge components are considerably lighter than the concrete components. In fact, many times, a backhoe can install a steel bridge. For steel bridges, the dead load is significantly lighter, and the lighter abutments can be used. Or some of the economical modular abutment systems can be employed, such as geosynthetic reinforced soil systems. Another benefit for the economy of steel bridges is the use of partial depth precast panels or corrugated metal deck systems that make the casting of the concrete deck efficient. We know that steel is a versatile material and that steel bridges can be made in many forms with complicated details in fabrication. However, these simple bridges do not require complicated stiffener or complicated diaphragm details. Simple details are cost-effective and easy to fabricate and easy to erect. Another costly component for bridges are rocker or pot bearings at the girder ends. Again, for these simple bridges, simple elastomeric bearings can be used and smaller bearings used due to the lighter weight of the structure. Also, jointless decks with integral abutments leads to much lower deterioration rates and maintenance costs in the future. Finally, one of the costs for steel bridges is corrosion protection, since regular steel rusts. However, weathering steel, when applicable, is low cost and requires little maintenance for long-term corrosion protection. If weathering steel is not applicable, galvanizing, metallizing, painting, or the use of stainless steel may be a cost-effective method for corrosion control. So that was one example that Dr. Michelson showed last week, and we went into more detail here to show the competitiveness of steel. However, that was just one example, and like Dr. Michelson did last week, I'm going to show this table. Because the Alliance also worked with the county engineer on other bridges built near the same time frame in the same county. This table looks at the total constructed cost. We were not able to look at only superstructure of an additional 5 steel and 4 concrete bridges built in Audrain County. At the bottom of the table, we see that sometimes steel is less expensive and sometimes concrete is less expensive. This is healthy competition, and this competitiveness is good for the owner and the public. These are examples of county bridges that show that both steel and concrete are competitive in the short span market, and both should be considered. The Short Span Steel Bridge Alliance has many more similar examples that are not shown here due to time. So these examples were county-owned bridges. Next, we will look at a couple state bridges, also in the state of Missouri. Here are 2 nearly identical bridges, one steel and one concrete, that cross over the same highway near Columbia, Missouri. Both are 2-span with a concrete bridge just a little longer and a little wider, so the total cost will be divided by the deck area, again, for comparison. These were both design bid build projects with a contractor constructing the 2 bridges. Here are the costs for the 2 bridges. Both had non-bridge items such as conduit systems, a pedestrian fence, and an architectural facade, and these costs were removed from the total costs and say are not structural. We see that the concrete bridge costs $77.71 per square foot, and the steel bridge costs $72.94. However, there was a 5-year difference in when these 2 bridges were built. So what I did was, to account for the age difference and inflation, an Engineering News Record construction cost index of 2.7% per year was used to bring the cost of both bridges up to a common year of 2017. We see that the steel bridge was less cost at $85.58 than the concrete bridge at $91.18. Again, and not to pound on this too much, but again, 2 nearly identical bridges, this time state bridges, that show that steel is competitive with concrete. So what we have seen here, and with many more examples I could have shown but have not, we see that steel is competitive with concrete bridges in the short span market, and that owners and engineers should consider both materials for their bridge needs. The preconception that concrete is less expensive than steel in the short span market is a misconception. Both steel and concrete is competitive, and competition is good for the owner and the public. So moving on, first cost is just that, the cost for putting the bridge in place. Responsible owners are also concerned about future maintenance costs and service life. The question about life cycle costs routinely comes up as we talk about steel bridges across the country. Actually, what is asked is, which type of bridge is best for life cycle costs? And both the steel industry and the concrete industry has offered anecdotal evidence, but has not, until now, had good evidence on which bridge type is best. So a study was conducted that examines the historical life service, meaning the performance and maintenance, and agency life cycle costs, meaning the true cost for building and maintaining the bridge over its life, of typical steel and concrete bridges in Pennsylvania. A historical study was conducted so that the results showed what actually happened to the bridges instead of anecdotal guesswork from the steel and the concrete industries. The Pennsylvania Department of Transportation had good records and their bridges on their bridges and offered the PennDOT data for the study. To determine the life cycle cost for a bridge, one needs to know the full history of that bridge. This includes the initial cost and the year it was built, and all maintenance that occurred over the life, including departmental maintenance and contractor maintenance. And of course, the lifespan for the bridge, or when it will be replaced. All of the bridges in the PennDOT database were still in service, so an end-of-life model was needed to estimate the life of the bridge. The study's objective was to compare life cycle costs of typical concrete and steel bridges. So there were criteria that each bridge had to meet to be included in the study. The criteria included considering only typical steel and concrete bridges, where that was selected as precast I-beam, precast box, where the boxes were adjacent to each other, precast boxes, where the boxes were spaced apart, steel rolled beam, and steel plate girder bridges. In addition, precast concrete became a mainstream construction method, and modern steel design and detailing started in about 1960. So bridges built after 1960 were considered. Each bridge that was used in the database had to have complete records for initial costs and date built, and accurate dates and costs for any type of department or contractor maintenance. Since the study was looking for typical bridges, it removed any bridges that had exceedingly high or low initial costs. And all the costs that were used were based on the PennDOT recorded costs. PennDOT has over 25,000 bridges in their database. Of those, almost 8,500 were of the 5 types considered in the study, and of the 8,500, over 6,500 were built between 1960 and 2010, the end date of the database, for a potential study database. When the 87 bridges were subject to the criteria, many of them did not have accurate and complete life history information, which left a database of a little over 1,700 for the life cycle cost study. This, as this table shows, this is over 25% of the potential bridges represented in the life cycle cost study, which is a pretty good representation. All of the 1,700 bridges are still in service, so a bridge life model needed to be developed to predict when the bridge would be taken out of service or replaced. The model is based on the inspection superstructure condition rating, which of course varies between 0 and 9, 9 being a perfect bridge, 0, I guess, meaning it's no longer there. And it was assumed that the bridge had a rating, a superstructure rating of 9 when it was built. Then a deterioration was determined based on the condition rating in the year 2014 by the change in rating divided by the years in service. With the deterioration rate, the remaining life could be estimated by assuming the bridge would be replaced when the superstructure condition rating became a 3. And the bridge life is the sum of the remaining life added to the current age. Now, I understand this is just a linear deterioration rate, which we understand is not completely accurate. And we looked at some other deterioration models from PennDOT where it was bilinear, where deterioration increased faster at the end. But what we found that it didn't matter, that it didn't change any of the comparisons, and the linear rate was so much easier to apply. This is the first results table from the life cycle cost study. It shows the average deterioration rates for the 5 types of bridges for not only the 1,700 bridges in the study, but the over 8,500 potential bridges. For this presentation, when these result tables are shown, there will be two aspects of the results mentioned. First, the top two best performance types of bridges will be highlighted. Here you see that at the bottom right. And for instance here, steel rolled beam bridges have the lowest deterioration rate of 7.1% of a condition rating per year, and precast spread box bridges is second with an 8% deterioration rate. The second aspect is the statement at the bottom left that all are similar with none way out of balance. The results show that the deterioration rates for all 5 types of bridges are not far off from each other. There is no one type of bridge that greatly outperforms the others, nor is there a type that is significantly less than the others. We will address this statement, all are similar with none way out of balance, towards the end of this presentation. Now we will look at a life cycle cost analysis of an example bridge that demonstrates the work of the study. The bridge is a precast spread box bridge built in 1969 with 3 spans and a deck area of 7,600 square feet. In 2014, the base year of this study, the superstructure condition rating was a 5. Knowing the average deterioration rate for spread box bridges is 8%, the estimated remaining life when the condition rating reaches a 3 is 25 years. Given that the bridge is 45 years old, the predicted lifespan for the bridge is 70 years. The top of this slide shows the actual years and the actual costs during those years for the initial construction and the maintenance over the lifespan. The actual costs are divided by the deck area for comparison to other bridges. To compare life cycle costs over the database, inflation must be taken into consideration. So all of the bridges were assumed to be built in 2014, and all of the costs inflated by the Engineering News Record construction cost indices, like we saw for the earlier case study. So this bridge in 2014 dollars costs $143.45 per square foot, and the maintenance costs in 2014 dollars occurred at years 19, 40, and 44. The study used constant 2014 dollars for all future costs, since the discount rate considers inflation for the future. Now the life cycle of the bridge can be developed with the dates and the costs in 2014 dollars. Using a discount rate from the Federal Office of Management and Budget of 2.3% that takes into consideration inflation of the future 2014 dollars, a present value cost of the bridge's life cycle can be determined to be $154.50 per square foot by discounting the future cost to the year 2014. This means more or less, if $154.49 was put away when the bridge was built, the amount could pay the initial cost and all future costs for that bridge cycle. However, we cannot compare the present value cost of a bridge that lasts 70 years to a bridge that lasts only 40 years or one that lasts 90 years. The outcomes are not equal. And a way to compare different life cycle or lifespan bridges is to use perpetual present value cost, also called capitalized cost, by assuming the bridge is replaced after each cycle in perpetuity. This is the same thing as doing equivalent uniform annual costs, but those are just harder to understand than capitalized costs. So for this bridge, the capitalized cost, when we replace that bridge every 7 years, is about $194 per square foot, which means again that if that amount was put away today, it could pay for the first cycle bridge and replacement of that bridge every 70 years forever. Now with capitalized costs, we can compare all of the bridges in the database directly. To further make sure the study compared typical bridges for the 5 types of bridges, bridges that had capitalized costs outside of 1 standard deviation from the mean of that bridge type were removed. This is one of those statistical things we do, but If I considered all of them, the results didn't change at all. But we still did this. This left almost 1,200 bridges of the 5 different types that were used to study the results. So we did all those on all those 1,200 plus bridges, and the bridge database was organized by bridge type in 3 Excel worksheets for each type. The first worksheet was the bridge information with location, years built, number of spans, bridge length, deck area, geometry, and bridge materials. The second file was the department and external contractor maintenance performed on the bridge. And the third was the initial and life cycle cost results. Studies of the final report were produced from this database of bridges. The report considered bridge life and capitalized costs, where the capitalized costs were studied for several variables as shown here. Bridge life, number of spans, bridge length, present value cost of future costs, just looking at departmental maintenance, just looking at external contracts. Also for steel bridges, curved versus straight bridges, fracture critical bridges, and protection systems. For this webinar, we will look at bridge life, capitalized costs for the entire database, and capitalized costs for the short length bridges as shown in blue here. But the full detailed report can be found at www.shortspansteelbridges.org. An additional study after this first one was completed was performed to look at the life cycle costs of galvanized steel girder bridges, and that report can also be found at the website. So now for some results. For the results for bridge life, the database of the 5 types of bridges show that the roll beam bridges have the longest predicted life at over 81 years, and the second was the precast spread box bridges at just under 80 years. However, again, none of the bridge types varied much from the others with a 7-year spread, and at the bottom is that statement that all are similar with none way out of balance. So that's the average. Maybe a better way to look at predicted life that considers not only the average life, but also the standard deviation of the life is a statistical cumulative density function, or CDF. Here it is assumed that the data is normally distributed, and it kind of was. And with the CDF, the question can be asked, what is the probability that a type of bridge, will last at least 75 years, which is the expectation for modern bridge construction? The results here show that there is a 73% chance that a rolled beam bridge will last at least 75 years, and a 65.6% chance that a precast spread box beam will. However, it also shows, according to the data, there is only a 44.3% chance that a precast I-beam bridge will last 75 years or more. Moving on. This table shows the results for capitalized costs for all the bridges in the database. Here we see that the precast I-beam bridge has the lowest capitalized cost, and the steel roll beam is second. The table also shows the initial cost, present value costs of future maintenance, average length, average number of spans, average year built, and average life. This is where we need to be careful with the comparisons. Directly comparing all of the bridges without considering the differences in these variables can lead to misleading results. For instance, plate girder bridges in the database have an average of over 4 spans per bridge, whereas the adjacent box precast bridges average just over 1 span per bridge. Number of spans, along with average length of the bridge, has a significant impact on costs. In a couple of slides, we will examine a more consistent set of bridges based on span length for a more consistent comparison. And of course, the full report examines these different variables in depth. However, for the full database results, we can again use the cumulative density function again to ask the question, what is the probability that a bridge type has a capitalized cost less than $300 per square foot? And the results show that there is a 93% chance that a precast I-beam and an 88% chance that a steel rolled beam bridge have capitalized costs less than $300 per square foot. Okay, now moving on. The short span steel bridge alliance defines short span as simple spans 140 foot and less. And I had to show this slide because this webinar is being sponsored by the Short Span Steel Bridge Alliance. So this table reduces the full database to only bridges with lengths of 140 foot or less. It does not restrict it to simple spans, but only by the length. In the full report is one that looks at just simple spans. There is much more consistency in the average length and average number of spans, which makes a better comparison than the full database results. Here, we see that steel rolled beam bridges has the lowest capitalized cost at $266.24, with precast spread box bridges at $272.64 per square foot. However, there is still that statement that all are similar with none way out of balance on the bottom left there. Now, the plate girder bridges here are a little high, but that would be expected in these short spans since they are not as economical below about 80 feet, and many of these bridges would be below 80 feet. So now we're ready to get back to that original question from owners of which type of bridge is best for life cycle costs? The precast box adjacent, the steel plate girder, the precast box spread, the precast I-beam, or is it the steel rolled beam bridges? And this is where we come back to that statement that all are similar with none way out of balance. The overall weighted average capitalized cost for the 5 types of bridges is $252.40 per square foot. If we look at the averages for each bridge type, that is within 14% of that weighted average. Now, knowing that the standard deviation for the different bridge types range from $48 to over $65 per square foot, or a better way to look at that is the coefficients of variation range from 20 to 25%. When we compare that to a variation of the means of only 14%, what that means is that any one type of bridge may be most economical for a particular given bridge project, that there is no one type of bridge that clearly beats the others. So the conclusions of the life cycle cost study are: typical concrete and steel bridges are competitive. And what we saw is they're competitive on initial costs, future costs, life cycle costs, and bridge life. For any given bridge project, concrete or steel bridge types may be the most economical. Again, that preconception that concrete is always less expensive than steel is a misconception. And finally, and it's even bolded here because this is my #1 conclusion, is that owners should consider both steel and concrete alternatives for individual bridge projects. Competition between steel and concrete bridges is healthy for the bridge industry, the owner, and the public. So that concludes the short span bridge economy and life cycle costs webinar. Next week, the last one in the 7-part shelter in place webinar series, where it concludes with a presentation on hot dip galvanized steel bridges. I thank you for attending this 6th webinar in the 7-part series. If you would like more information about the Short Span Steel Bridge Alliance or on the topics in the series, you are certainly encouraged to visit the shortspansteelbridges.org website or to contact the Alliance directly. Have a wonderful week and stay safe.